Here we are going to discuss binary liquids and its properties. So binary liquids means the combination of two liquids. When two liquids combine together, three possibilities are there. The first one is these two liquids are completely miscible. And the second possibility is that these may be partially miscible. Then the third probability is that these two liquids are immiscible. First of all, we are going to discuss the properties of binary liquids which are completely miscible. So here we are going to consider the completely miscible liquids. So here we are going to consider the mixture of completely miscible liquids. Consider a particular gas is filled in a container. Here this vapor molecules always move here and there, and this gaseous molecule will exert a certain pressure on the walls of the container, and that pressure which is exerted by the vapor molecules on the walls of the container is known as vapor pressure. So here consider we are taking particular liquid in a container, in a closed container. So here we are taking a liquid substance in the container. After some time, what happens is this liquid substance started to evaporate. That means now the system is filled with the liquid as well as the vapor of the same compound. And the gaseous molecules formed from the liquid substance will start to condense and converted back into the liquid form. So these two processes will occur within the same container. So at a particular time, the rate of evaporation will be equal to the rate of condensation. This system is in equilibrium. So here also the gaseous molecules, the vapor molecules of the liquid will exert pressure on the walls of the container, and we can call the exerted pressure as vapor pressure of liquid. So here this is the vapor pressure of liquid. This entire system is placed at a temperature T. So we can define the vapor pressure of a liquid is as this the pressure exerted by the gaseous molecules on the walls of the container in equilibrium at a given temperature T. In equilibrium means in equilibrium between the vapor and liquid at a given temperature T. So if we consider a binary liquid having two liquids A and B, then the vapor phase exists within the container contain both A and B vapors. So here this is a binary liquid So here the partial vapor pressure of the component will be equal to the vapor pressure of the pure components into the mole fraction of the component. So we can say the partial vapor pressure of A equal to P0A into chi A. Here PA is the partial vapor pressure of A, and the P0A is the vapor pressure of A, and chi A is the mole fraction of A. Same way, PB equal to P0B into chi B. This is known as Raoult's law. So Raoult's law can be stated as, at a given temperature, the partial vapor pressure of a component is equal to the product of the vapor pressure of the pure component and the mole fraction of the same component. So Raoult's law can be defined as, at a given temperature, the partial vapor pressure of each component is equal to the product of the vapor pressure of the pure component and its mole fraction. We know ideal gases means the gases which obey ideal law. Same way, ideal solution means the solutions which obey Raoult's law. So if we consider an ideal solution, that is, we're going to mix two liquids A and B. So here, in this ideal solution, the interaction of all the molecules are same. That is, interaction of AA equal to interaction of BB equal to interaction of AB. So in an ideal solution, the interaction between all the molecules or the force of attraction between all the molecules are same. And for the solution, the delta H mixing and the delta V mixing, etc., are equal to 0. That is, delta H mixing is equal to 0. Same way, delta V mixing is also equal to 0. That is, there is no heat change during the solution formation. There is no heat change during the mixing. And there is no volume change during the mixing. No volume change. Benzene toluene, then N-hexane, N-heptane, N-hexane mixtures are considered as ideal solutions. So now we are going to consider the vapor pressure composition curve of ideal solution. We know the partial, if we consider a mixture of two liquids A and B, then here the partial pressure of A equal to vapor pressure of the pure component A into mole fraction of A. Same way, partial pressure of B equal to vapor pressure of B into mole fraction of B. And we know mole fraction of A plus mole fraction of B, or the total mole fraction of a mixture is unity, that is equal to 1. So I'm going to mark this is equation number 1, 2 and 3. So then if chi A equal to 1, that is I'm considering the mole fraction of the component A equal to 1, then PA will be equal to P0A. Anyway, if chi A equal to 0, then PA will be equal to 0. Since here PA into PA0 into 1, that is why this is P0A, and here P0A into 0. So if I plot a graph, x-axis is small fraction and the y-axis is vapor pressure, y-axis is vapor pressure. If I am plotting mole fraction of A here, that is mole fraction of A from 1 to mole fraction of A equal to 0. So here in the vapor pressure axis, I'll get certain value PA, and when chi A equal to 0, the vapor pressure will be equal to 0 for the A component. So if I draw the graph, this will be appear like this. So instead of A, if I am considering B here, so when mole fraction of A equal to 1, from this equation, if chi A equal to 1, then obviously chi B will be equal to 0. Then only we will get the value 1. So when chi A equal to 1, chi B equal to 0. So here PB equal to 0. Same way, if chi A equal to 0, then chi B will be equal to 1. So PB will be equal to P0. If we plot the values of B in this graph, we'll get here chi A equal to 1. So chi B will be equal to 0. So chi B will be equal to 0. Then here chi A equal to 0. So chi B equal to 1. So when chi B equal to 1, we will get a certain value for PB, that is PB0 here. So here I am going to consider this is as PB0, vapor pressure of PB, and when chi B equal to 0, we will get the value here. So if we join these 2 points, we will get a line like this, a straight line like this. Here PA0, partial pressure of A. Okay, this is the graph we'll get from these calculations. So from this graph, it is clear that the total partial pressure of this graph will be equal to the sum of these two. Partial pressure P of the total solution will be equal to PA plus PB. And it is given by Dalton. So it is known as Dalton's law. So we can define Dalton's law as the total partial pressure of the composition will be equal to the sum of the partial pressures of the components. That is, let P is the total partial pressure of the composition, and PA and PB are partial pressures of the components. Then total partial pressure P will be equal to PA plus PB, and it will be equal to PA equal to P0A chi A plus PB equal to P0B chi B. We can write simply like this: P equal to summation of Pi, where Pi equal to P0I chi I. This is vapor pressure composition curve of ideal solution. If we consider any composition of AB mixture, then the partial pressure will be lies within this curve. That is, it lies between the values of PA0 and PB0. And see, here we got straight lines, but this is not same for real solution. No surety that we'll get a straight line in a real solution vapor pressure composition curve. So we have to study the vapor pressure curve for real solutions also. Okay, now vapor pressure composition curve of real solutions. So real solutions means non-ideal solutions, non-ideal solution which shows deviation from Raoult's law. So that means here in real solutions, the partial pressure of the components either greater than or lesser than what we predicted in Raoult's law. It's greater than P0I chi I or lesser than P0I chi I. And they may show slight deviation from ideal solutions or may show large deviations from ideal solutions. So they may show slight deviation or large deviation. So the real solution which shows slight positive deviation from the ideal gas solutions can be called as type 1 solutions. Large deviations may be of two types. One is large positive deviation showing real solutions, and the next one is large negative deviation showing real solutions. So we can call this as type 2 solutions and this as type 3 solutions. So let us discuss the real solutions of type 1. Here in real solution, the partial pressure of the components is slightly greater than the partial pressure of the components in ideal solution. So partial pressure of components is in real solution is slightly greater than in ideal, slightly greater than in ideal solution. And the most common examples are benzene toluene, or benzene carbon tetrachloride, benzene CCl4, or cyclohexane CCl4 mixtures, etc. So here the vapor pressure composition curve will be like this. Here mole fraction, and in y-axis it is vapor pressure. So for ideal gas, we'll get a graph like this. This is the graph what we obtain for ideal solutions. But if we consider a real solution of type 1, for example, cyclohexane CCl4 mixture, shows slight deviation from ideal solution vapor pressure composition curve. That is we show a slight deviation like this, and the total vapor pressure for ideal solution is this, and our real solution is almost close to the ideal solution plot. All these are straight lines. All these are straight lines, okay. See, only slight differences from ideal solutions. So we can say the enthalpy of mixing and volume of mixing is almost equal to 0. And the total partial pressure will be lies between the partial pressures of the single component cyclohexane and the CCl4. Here, if we consider any composition, then the partial pressure of the composition will be lies between the partial pressures of the single components. The next one is type 2 real solutions. Here, it shows large positive deviation. That is, the total partial pressure of the real solution is greater than what we predicted in Raoult's law. That is, we can say P total is greater than P0A chi A plus P0B chi B, if you are considering the binary liquids of A and B. Why this solution shows positive deviation? Because the interactions of the components in the binary liquid is not same. In real solutions, the interaction of AA equal to BB equal to AB. But this is not true for these type of solutions. So here, the type 2 solutions, the interaction of AB is lesser than interaction of AA and interaction of BB. So here the interaction between the difference components is lesser than the interaction between the same components. And here the enthalpy of mixing and volume of mixing are greater than 0. So these two are greater than 0. That is, enthalpy of mixing and volume of mixing are positive values. So examples are water propanol binary liquids, water propanol, acetaldehyde carbon disulfide, etc. So here we can draw the graph for ideal solutions like this. So, and this is the total partial pressure. So if we consider the binary liquid acetaldehyde carbon disulfide. Then here acetaldehyde. And here carbon disulfide. So here these components, that is acetaldehyde and carbon disulfide, shows positive deviation from what we expect. That is, their partial pressure will be large, will be highly, will be very much greater than, will be very much greater than what we expect. Partial pressure of single components increases means the partial pressure of the total binary liquid is also increases. That so the total partial pressure appear like this. First of all, it increase and attain a maximum, then started to decrease. So this is the total partial pressure of the real solution. That is why we told here partial pressure P total is greater than P0. P0A chi A plus P0B chi B. So this here the total partial pressure P total is discontinuous. That is, increases slightly, attain a maximum, then decreases. So it is discontinuous. But in the type 1, for type 1 it is continuous. Okay, type 1 continuous. Type 1 shows continuous partial pressure graph. Then moving on to the third type, that is solutions, real solutions showing large negative deviation from ideal solutions. So here P total partial pressure will be less than P0 A chi A plus P0 B chi B. Because this interaction between the different molecules are greater than the interaction between the same components. That is, AB is greater than AA interaction and AB interaction is greater than BB interaction. And here the delta H mixing and delta V mixing, enthalpy of mixing and volume of mixing is lesser than 0. That is, these attain negative values. Examples are toluene acetic acid mixture, then acetone chloroform mixture, etc. So here the graph will be like this. For each single component shows negative deviation, that is, their partial pressure will be largely lesser than what we expect in ideal solution. Here also same way the total partial pressure will also lesser than total partial pressure of ideal solution. That is why P total is lesser than P0 A chi A plus P0 B chi B. Here also this P total is discontinuous. First of all, it decreases and attain a minimum value, then increases. And this is the curve of acetone chloroform. So these are all about the volume composition curve of real solutions.